school for the high school students. So you see a lot of high school students around. I think you already saw it in the coffee break of the coffee line. Yeah. But today the first lecture is going to be by İnanç Arın, who is also an assistant professor here in Sabancı. And then he's doing a lot of really good work on, like he's teaching now LLMs and also like the applications and the theory of it. So I'm teaching NLP, like more like the basic, more like classical NLP techniques, and then Nantuda takes it off and then gives more details on LLMs and applications, and then the foundation. So you're in the really good hands to start off this summer school, and hope you can get really good information. But I'll leave it to you to also introduce yourself, and then we'll start. We can start the lesson, and then we'll have around 2 hours of lesson, and then we'll I'll meet you at lunch.
Okay. Thank you, Hocam. First of all, welcome everybody. I'm very happy to be here for today's lecture. First of all, I would like to thank Dilara Hocam for inviting me for this special lecture. I would be more than happy for being here and teaching you guys. So here is my name, my email name. In case of any need, you can always reach me out and we can exchange our information and so forth. Today, actually, I will give you a very short chapter because we only have 2 hours lecture. As Dilara mentioned, I'm teaching LLM course in Sabancı University. Actually, in this semester, we offer this course for the first time in Sabancı University. Actually, and Ali here? Okay, Ali has taken the course recently, just finished the course. So in today's lecture, I will be giving you the 1 chapter of this course, which is about semantic search. First, I will give you the basics about the importance of why semantic search is important, and then I will give you some theoretical background together with some practical application with real data. That will be the topic of today.
I heard it was a really hit course from my students. They all liked it, so I think you'll really enjoy it today. But I'll leave it to you, and I'll see you over the lunch here. Bye.
Thanks, my friend. Okay, guys. First of all, if you want to read access my lecture notes for today, so this is my drive folder. What I'm gonna do, guys, I'm gonna share with you right now with a QR code. You don't have to, but if you want, you can just read this QR code. It should be public accessible right now. Yes. Does it work? Yes. Okay, great. So once you log in or once you access what you're gonna find, first you will find an HTML file that I will go over in today's lecture. So you will find this HTML file first of all, and also you will find a collab file right in there. Right now it's empty. Hopefully at the end of the lecture we will figure this out all together. So it will be a live coding lecture, right? So I just want to make this more practical for everyone. I don't know whether your background is appropriate for this or not. I assume that you know Python. I assume that you know some basics of large language models. That's all. So we can start with this HTML file. Once you download and open this HTML file, you will find something like this. As I told you guys, I will start with semantic search and then give you the basics of or fundamentals of semantic search. Okay, let's start. Let's start with the first subchapter of this. Why semantic search is important. So, first of all, search is a very fundamental problem in real world. So we are actually, whether you're aware or not, we are making too many searches in our daily lives and also in our professional lives as well. So here, whenever you want to make a search, traditional methodologies may not be enough for you guys. What are traditional methodologies? These are either TF-IDF, meaning that term frequency and inverse table frequency, or you can use more advanced methodology like BM25, which is best match 25, all right? These are good methodologies, but these are like making some keyword searches. So as long as you have an exact keyword matching, that's okay. They work perfect. However, if the keywords are not matching in your query and other documents that you are searching for, then you have a problem. But I will give an example here. For instance, look at that example. I don't know whether you watched the movie Interstellar. This was a very famous movie. I think it was released in 2014, something like that, right? Anyway, it's not important. The Interstellar is a science fiction movie. And also there are a lot of debates about how science was precise within this movie. Assume that the user asked this question: how precise was the science? So in order to answer this question, we have some set of documents, right? There are some posts, some Wikipedia articles, some other information related to the movie, and we are searching for the answer to that question. So the best matching document should be like this. Please read that answer, okay? You will see that within that answer, you do not see anything precise, anything science. But instead, what you're going to see, you will see accuracy, you will see scientific, for instance. So these two keywords, or how precise science, they never exist within this best matching document. So if you just apply traditional methodologies like BM25 or TF-IDF, then you will not be able to find this best matching document in your results. So that's the problem that semantic search wants to solve, right? That's the idea. Instead, what we want to do, we want to embed this query and this document along with the other documents into a vector space. What we're going to have within this vector space, we want to carry the semantic information of all of these documents. So by capturing the semantic information or semantic meaningless, and then you'll be able to find the relation between that question and that document will be quite high, so that we'll be able to capture or find these related documents. That is actually the importance of semantic search. Actually, even Google, Bing, and other search engines also use semantic search, and they must use, otherwise, because we are not just, whenever you ask a question to Google, actually we are not exactly typing the exact keywords that we are looking for. For that reason, they must apply this kind of semantic search. So, actually, in the scope of this problem, I will propose you three different solutions. First, bi-encoder. In other words, it's also known as dense retrieval, right? And then I will talk about cross-encoders. In other words, it's also known as rerankers. So I will also talk about what are the differences between these two methodologies, what are the advantages, disadvantages, when to use which one, and then maybe how we can combine them to each other just to implement and hybrid application, so forth. And latest, maybe you can use another LLM just to generate a human readable answer by looking at the answers coming from these encoders. All right. Actually, this is then known as a RAG application. RAG means Retrieval-Augmented Generation. So first, I will start with bi-encoder, which is the dense retrieval. So what bi-encoder does? Bi-encoder is actually a neural network structure. It is generally based on BERT or Roberta-based autoencoder large language model. By the way, before I go proceed further, I just want to distinguish two different large language model methodologies. First, autoencoders like BERT, Robert, Albert, so forth, Roberta, Albert, so forth. On the other hand, we have autoregressive models like GPTs, Llama, Duet, some other. These are some generative models in that people use in daily life more frequently, but it doesn't mean that autoencoder models are not important. These are also very important, and what what I'm going to talk about with bi-encoder or cross-encoder, we will be using these autoencoder models, okay? BERT, Roberta, or some similar models that we can utilize within this application. So what we're going to do here, guys, as you can see, in the heart of this bi-encoder, we have a pre-trained transformer model like BERT or Roberta. Generally, we use both, one of them. Generally, we use Roberta actually, to be honest, because it's more advanced and much work much better. First, whenever you ask a question or whenever we have a document, what we're gonna do, we tokenize this, meaning that we distinguish this text into pieces of text, all right? And then we convert them into embeddings, which are some vector spaces for each token. And then we send them to the transformer layers in order to understand their contextual representation. So that if you have a bank keyword within your sentence, so we will be able to understand whether it means bank account or it means a riverbank, thanks to the attention mechanism implemented in transformer architecture. And then at that, you will see that in a minute, we will have vectors for each token. Now we need to decide how we can aggregate all of this information. Whether we will apply a mean pooling or max pooling, or maybe we're going to use the spatial token embedding, which is CLS token, so on so forth. We have to do that. And normalization, all they say is optional. Actually, it's not optional. I'm going to talk about it in a minute, but we have to apply normalization just to perform, just calculate symmetric scores in a much more accurate way. However, it's optional because depending on the model, some models automatically normalize the scores at the end, but some models, they do not automatically normalize the score, so that we have to do that manually. So I'm going to show both of these models together in today's lecture. So let's come here. Look at here. Actually, that is your query. Remember, it's the same query that I shown you in the previous part. How precise was the science? First, we have to tokenize this. So once we tokenize this, of course, it depends on the model that you are using here. It's not we are using BERT here. So this is the result of the tokenization process. These are two special tokens, CLS for classification, SEC or separator is another special token. They have some meaning. This CLS token represents the whole sequence in a BERT-like model. On the other hand, SEC has two meanings. The first meaning is it is the end of the sequence, or it is the separator between the first sequence and second sequence, because in some scenarios we might have two different sequences. So there must be a SEC token just to separate these two sequences over here. Okay, we first tokenize this, and then what we're gonna do? We send them all together into a BERT or Roberta encoder model. Okay, and then there will be some set of layers here. Generally, we have 12, 24 layers depending on the architecture. I assume that we have 12 layers for the base model. We have some hidden dimensions, so that at that we will have again the embeddings of these tokens. But what is the difference? So there will be a difference between this embedding and this embedding. What is the difference? These are contextless embeddings. On the other hand, once you proceed over this BERT model, these tokens or these embeddings will be contextful, meaning that we just carry the semantic information, not only semantic information, but also by looking at the attention mechanism, we will be able to understand what is the context of this token right in here within this given context. While there is a mistake here, it has to be signs, there should be matching, and this has to be precise. Sorry about that. And the dimensions of each of these vectors will be 768, actually depending on the architecture, but in most of the architecture it will be 768. So, and then we have all of these vectors. It's a vector, another vector, another vector. Now, how we can aggregate them? There are different methodologies. The most common methodology is calculating their average. Okay, calculate average of each of these vectors in order to create one final vector that represents the whole sequence, right? On the other hand, the other methodology can be just use the vector of the CLS token. Actually, CLS token is classification token. Some people argue that this is not the best way of you doing this because this CLS token was not trained on to perform actually semantic search, so that it might not perform well. For that reason, people generally use average pooling or some other pooling methodology rather than using just CLS. Right. So we also do this for the documents as well. We also convert them into tokens and then pass through the actually the encoder model. At that, we're gonna get the result and then calculate the meaning, so on and so forth. And then, so maybe in order to visualize in your mind better way, I will show it right here. Okay, assume that we have such a model. This is a bird model, let's say. So what we want to do here, guys, we just have a query, and then we first tokenize them. And each of these tokens represent another vector, as you can see, and then we pass them to our bird model. So there will be some set of layers here. By default, it is 12 layers here. And then for each token, we have a contextual representation of each token. So, I mean, the number of vectors here is same with number of vectors coming in the input form, right? But again, what is different? These are contextless, but these are contextual representations. Remember, this is the CLS token, special token. This is the set token, again, another special token. Between them, like how precise science, blah, blah. And then what we're gonna do, we will calculate their average just to create one final vector to represent all of these documents. This is just for query. And now what we're gonna do, we have some set of documents as well, like document 1, document 2, document 3, until document N. We have a lot of documents, maybe millions of them, maybe billions of them, right? What is the purpose here? We want to find which one of these documents are really similar to this given query. That's the question. For that reason, guys, what we're gonna do, we're gonna apply the same thing, the same procedure here to all of these documents in your database, all right? So for each of the documents, we're gonna calculate another vector to represent all of these documents for semantic meaning, all right? And then the question is, which one is the most similar? So how are we gonna calculate this? Actually, since this is a vector, this is another vector, another vector, another vector, we can simply use the cosine similarity. What does cosine similarity mean actually? Remember in that way, assume that this is your query vector, this is your one document vector. Actually, there will be an angle, let's say it's theta, right? The cosine of this theta will give you how these two documents are similar to each other. This is known as cosine similarity. As this theta angle gets becomes smaller or getting close to zero, it means that these two documents are more similar to each other. As you increase actually this angle, it means that they are quite different than each other, right? So in other words, the cosine similarity formula will be, let's say, document A or document B, let's say. Document A, dot product, document B, divided by their norm values. For that reason, if you calculate their normalization, the normal value of each vector, just calculating dot product will give you the similarity between these two differences. That is the idea. So that normalization is important. If your model, if your BERT model does not normalize the vectors at that by default, then you have to perform this normalization if you then apply a cosine similarity calculation rate. Okay. Actually, oops. That is the methodology. But the problem is, there will be, it must be actually, do not disturb, but for some reason, I make the call. Anyway. So, but the problems here, we have a lot of documents to compare. As I told you, maybe a million, maybe a billion. So, should we really calculate similarity between each of them one by one? No, you don't have to. There are some advanced methodologies called as ANN. ANN, it doesn't mean artificial neural network. Instead, it means that approximation nearest neighbor. So we are trying to find the nearest neighbor here. But instead, we want to apply an approximation of this methodology so that it will perform much more faster. Okay? Maybe I will talk about this ANN later. So let me come back here. If you can see, in order to calculate similarity, we apply cosine similarity. We have two query and document. First, calculate the product, divide them with their norm values, and it will be the similarity score between these two documents. So it can be, in the best scenario, it can be 1 if they are exactly matching or overlapping each other. In the worst case, it can be -1. It means that they are actually showing in an opposite direction. They're completely different matrix, right? So at that, as I told you guys, should we use mean pooling or we just need to use just CLS token? Meaning that either we need to average all of these tokens or we need to just use the CLS token to represent the whole sequence. Actually, it depends, but people generally use the mean pooling. That is actually the most common scenario in today's real world. So, actually, it's not just my idea. If you look at one paper, actually released in 2019, I guess, its authors show that the mean pooling generally outperforms CLS pooling. So that you can look at this paper later on. And this also they introduced SBERT, in the words sentence BERT models. So what does it mean? If you just type sentence transformer to Google, you will be directed to one official website, which is sbert.net. This is the official website for sentence transformer library, which is actually the most common library if you want to apply some kind of semantic search applications. If you click on here, you will see that there will be a documentation for you guys. And just below, you can see a usage here. These embedding models, these are actually, whenever you use sentence transformer, it means it's a bi-encoder, right? This is a bi-encoder. If you click on this reranker model, you will be using a cross-encoder that I will talk about in a minute. And then another type, sparse encoder models, but this is out of scope for our job. So let me come in here. So what I'm going to do actually, maybe at this point, let me open my collab file for a moment. All right, I will be using Google Colab in today's lecture. Let me connect this here. This is not important for now, so I will just skip this part. So I'm going to save this for the last part of the lecture. So let me run this, but will not be running this here right now. But it's will not be so cool. Let's wait for a moment. We have to make this comment. So while running, let me introduce you here. Okay, the problem was the last one. Okay. This is a dataset model from the Hugging Face. So in the second part of the lecture, I will be using this real dataset coming from Google actually. And then what's important here, I will be using sentence transform. And what here, I'm going to import sentence transform. Why I'm importing this? If you go back to the website, if you can see, if you want to use these models, then you have to import this dependency into project, correct? And then NumPy just for basic stuff. And this is actually this TQ2M is a library just to follow or just to see your progress in a much more as a progress part. You will see in a moment. Let me run that. So what I'm going to do here, guys, I want to go back to my queries here. First, let's download a model. Actually, there are a lot of models that you can use from the sentence transformer. In order to indicate which model you want to use, you have to use that keyword. Each model is being represented with a keyword. So this is one model that was specifically trained for question and answer pairs. So that if you want to find the semantic relation between questions and the possible answers, it's better to use that model, right? But if you don't have questions, then you may want to use another model coming from sentence transform. So right now, I think we download this. So this is my model. So what I'm going to do here, guys, just check this model. As you can see, within here, we have a transformer architecture. After that, we have a pooling layer, but in pooling mode is CLS token. So we are not applying average pooling here. Instead, we are just getting the CLS token at the end of this architecture. And for this architecture, this is the preferred way of doing this. But if you want to use some other model, for instance, if you go back to official documentation, what I'm going to do, I'm going to download this one. Be careful, this time the keyword is different, all right? This is another architecture. But what I'm going to do, I will not make this model. Let's make this model 2, second model right in here. Let's download this as well. Okay, we have downloaded this. Just check model 2 here. Okay, look at here, guys. Again, we have another transformer architecture. And then we have again a pooling layer, but be careful. This time it's not CLS pooling, it is mean average pooling right in here. And also one more thing, we apply normalization. So that if you're gonna use the second model, you don't have to normalize your results at the end. But if you're gonna use the first model, since there is no normalization, just before you calculate cosine similarity, make sure that you normalize these vectors. So these are maybe small details, but these are important details just to get the accurate answer at the end. Okay? And then what we're going to do here, guys.
So just one moment, I couldn't track the.
Sure. Sorry.
Yes, just one.
Please stop me if I proceed a bit fast. These guys never stop me during the lecture because they were not typing, they were downloading.
Don't even copy.
I know.
I'm trying to improve my typings. Yes, okay.
So it's easier to use the normalized model.
Sure.
It's easier to use the model with normalization.
I mean, it's not about whether it's easy or hard. It's about which one, which model works better in our case. Sometimes, yes, this model, we prefer to use that model, even if it doesn't have a normalization process, because this model may work better in our scenario. So that you will see that this normalization is not a big deal. We will do this in one single line, but more importantly, we need to test in a correct way which model is being working actually in our database or for example. Okay. So what I'm going to do here, guys, in our lecture notes, if you go to my HTML file, you will see some set of documents here. This is my corpus here. I just copied it from here to here. Right now, I have, okay, this is one document, okay, until here. And this is the second document, the third document, so on and so forth, okay. Right now, yeah, I don't have many documents, just let's see how many of them. I think 8, right? Yeah. There are 8 documents, but I just want you to give basics behind this process, and then we will get much more bigger data sets. So what I need to do here, guys, so doesn't matter which one, okay, let's use the first one. Model dot encode, right? Once you use encode function, then you have to provide this corpus here. Once you run this, you will get a result. The result will be, okay, let's say that this result or embeddings. Let's look at the shape of embeddings. The shape will not be surprising for us. It is 2-dimensional because there are 8 documents. For each document, we represent them with a vector with dimension 768. So that each document coming from here will be represented with a vector. So this vector hopefully will carry enough information in terms of semantic meaning. That is that.
I got a different result. Is it?
Sorry?
I got 8,384.
Is that because you are using the second model? Because I have 2 different models. The first model was multi-query or
Sorry, yes.
Okay, I can also show this to you. That's a good question, by the way. You're right. If you're gonna use the second model, you can get another dimension just because of the architecture, right? Because the architecture coming from this model is quite different than the architecture from this model, right? Now, vector dimensions can be different as well. Not all the time, but I'm just speaking in general way. Once you have a higher dimension for a vector, generally you carry more information. Okay, you store more information in your vector, but it's not all the time. You have to test this, but still we carry more information here. So, okay, right now I'm using the second model. Or okay, if you want to use the first model, you have to rerun this. And then what I want to do, at the end of my notebook, there must be a question. Okay, so let's ask this question. This will be my query. This is the query. How precise was the size? Okay, and I want to find the similarity between this query to the all other documents coming from my corpus. That is the question. But before doing this, I need to convert this into a vector as well. How am I going to do this? Again, depending on which model I have used previously, model.encode query here. I suggest you, even if you have only one query, provide them as a list, because we generally have multiple queries at the same time. The result will be one single embedding. So before I run this piece of code, I think you can estimate right now what can be the outcome here. So what do you expect about the dimensions? About shape at the result? An idea. Remember, the first one should be number of documents, the first dimension. The second dimension should be the dimensions for the vectors. So how many documents do I have right now? Only one. So the first dimension should be 1. What about second dimension? It's about the length of the vectors, since I'm using the first model, it should be 768. So the result should be 1,768. Let's verify this. Yes. So meaning that always try to make this kind of sanity checks, all right? So it will show you you're on the correct track, right? Okay. But something is important. Something important. Since we are using the first model, remember, do we have normalization process at 10 of the first model? No. For the second model, yes. But for the first model, no. So that the lengths of these vectors are not 1. How can we check this? We can basically use NumPy's linear algebra module, and there's a function called as norm. Just give me the norms of these vectors. Let's say I want to check the norms of the embeddings. One deep dimension. Okay, depends on your implementation. You may want to use that parameter as well. So let's check this. As you can see, guys, these are actually the norms of each vector coming from a corpus. As you can see, they are not 1. But if you were using the second model, let me go back here. If I rerun this, if I overwrite the embedding models, now rerun this, as you can see, they're all 1. Because the second model automatically normalizes them, but the first model, rerun the first model again, recalculate these norms are not 1. If you want to calculate cosine symmetry, you have to make sure that you have to normalize them. So that what I'm gonna do here, guys, I'm gonna update these values with this. So just divide each embedding value with their original norm value, so that the first vector will be divided by this value, the second vector will be divided by this value, so forth. At that, if I rerun this, they should all be 1, or very close number of 2. Okay. So right now, I just make sure that here these vectors are normalized, but it's not enough. I should also normalize the query embedding as well. I'm going to do this separately. Yes.
Maybe we can like hold on for 1 minute so
Yeah, sure.
that people can like
Of course.
who can't keep up. You cannot keep up.
I think that
Yes.
you can. You can as well. Okay. Another person, you can as well.
I can keep up, but I don't know where we are.
Okay, first I'm giving you the fundamentals, because in the second part of the lecture, I will introduce you a real data set. It's much bigger. There will be thousands of documents over there. Before diving into that data set, first I'm running with only with very small corpus with 8 documents and so forth. So I'm showing you how to calculate, how to find the similarity between your question and your documents, so that we can scale up later, so that we will be able to work on huge number of data. Right? That is that. Okay.
Maybe also like a parenthesis. So in previous years, when we did summer schools in computational social science, I think I mentioned this to some of you, so apologies if this is like the second version of this. The majority of our time was spent on teaching people coding, like coding how to use R, how to use Python and everything. And every single year, we had better and better and better applicants who actually came with these skills. So most people in this cohort have programming skills. Then we upgraded to, what are the fundamentals of computational social science? Text mining, text analysis, network graph, GIS, spatial mapping, and statistical methods that would allow us to use machine learning and AI in social sciences. This year, when we were building this program, once again, with like Overboro, Adam, maybe and so forth, we decided that everything computational social science is drifting so fast into large language models that we decided to make the general theme of the Summer Institute large language models. Because we are living in a world in which we use ChatGPT, Claude, whatever. We use it for coding, we use it for problem solving, we use it for like searching for information. And we think that throughout this summer institute, we are going to tackle this issue of social sciences of large language models in multiple ways. One, how to use large language models to do social sciences. Two, how to use human large language model interaction as a source of social data. And three, we really want to dig deeper into the mechanics of large language models in order to understand the statistical parameters and principles of how large language models work in principle. So this lecture basically opens up the entire Summer Institute. It basically gives us a more intimate look on the mechanics, the specifics of how large language models work. And I think using large language models in search setting is one of the best ways to do that introduction. So maybe
Search is a very well-known problem,
Yep.
and it's a very useful methodology about, like I told you in the beginning of the lecture, whether we are aware or not, we are using search a lot in our daily lives. It's not only about Google, it's not only about being in our other parts of our professional or specialized, we are making a lot of searches. Right? So search is a very common problem, very well-known problem. So that understanding the basics and understanding the methodologies behind the search will be quite useful in almost every domain, in almost every, including social sciences, including computer sciences. For that reason, it's a very common, actually, problem that is applicable to different various areas.
have you all caught up? Do you want the code again? Maybe like
Yes. Yes.
Hocam, can we
Sure. Maybe what is also, so there, I know that there are some computer scientists in the group among myself and Melissa and like Bill, for instance. So maybe if people are feeling like, oh, after today, we don't understand or we need some fine-grained knowledge on what, for instance, is a vector, then you can definitely also come to us and sit down and we can, or maybe we can team up for the research projects because then you kind of can work interdisciplinary and
Yeah, that's a good idea.
computer scientists get a little bit more of this political science, social science input and
that's the whole idea. That's why like
Yeah.
the group is so
So know where to find us. If you have questions about vectors, thank you. I'm here. I'm your gal.
That's great. You touch volunteers.
Can we like go from the top and like come down, like
Sure.
explain the codes, like so
Let's
that
start from beginning again. First, I have these imports just to make our code working. And then here, I have downloaded my first model. Okay, so this is the keyword of my first model. Remember that when you look at the first model, we don't have any normalization layer at that. And then I downloaded my second model just to show you the difference between the first and the second model here. So if you provide this keyword, you will be actually using the second model here. What is the main difference? First, the dimension is different. Secondly, the pooling mode is different. And thirdly, we have a normalization process at that by default, right? And these are actually ready to use two models in my code. And then I have a corpus. Corpus means set of documents. So I want to find some similar documents here. Remember how precise was the sign is the question. And then I want to find which document is the most similar to that question within my corpus. There are 8 different documents coming from my corpus. So you can check this out. This is the length of the length is 8, correct? And then by using the first model or the second model, it doesn't matter which one to use. You just need to specify the name of the variable correctly. Just use encode function to convert them into vector representations. So that this embeddings will be showing you the vector representations of all documents coming from my corpus. So this is the dimension of each vector for this model. This is the dimension of each vector for the second model. That is the idea. But I just want to go with the second model here as well. And then I need to convert the query into a vector as well. So again, I will be using same model. It's very important. You have to be consistent between the model to be used on the corpus and on the query. Right? Then convert them into embeddings as well. This is the shape of vector. And then don't forget to normalize them. Right now, we normalize the embeddings of the corpus vectors. However, don't forget to normalize your query vector as well. So what we're gonna do here, guys? I'm gonna take this. I'm gonna divide this with its normal value. So you can check this out. And then norm should be 1 as well. Good. So right now they are ready. Ready for what? Ready for calculating the dot product. In other words, since they are normalized right now, if you calculate their dot product, like basic linear algebra here, we are just calculating their cosine similarity between the question, query, and documents coming from my corpus. How I'm going to do this? You have to be careful. First of all, look at the dimension of this. And look at the dimension of the embeddings as well. It's very important. Why is it important? Because if you want to calculate dot product between this embedding or this vector and this vector, the dimension should be matching. I don't know with how much you remember from your linear algebra course, but remember that if you have one vector, that's matrix 1, dot product, matrix 2, right? Assume that the shape of this A and B of matrix 1. What about the shape of matrix 2? What should be? The first dimension should be B, because whatever the second dimension is, the first dimension of second matrix should be matching to each other. Otherwise, you will not be able to calculate dot product here, right? So these two should be matching. However, these can be different. These can be different than each other. But the resulting matrix will be A to the C dimension. So this will be the result of the dimension of the resulting vector. So what I'm going to do here, guys, in order to calculate the dot product, I need to transpose this. What does it mean? If you calculate transpose in a vector, you just change rows with the columns, correct? So if you can see, columns will be the rows will be the columns. You are just switching the dimensions here, so that you will be able to calculate dot product just in here. So what I'm going to do here, guys, for that reason, I need to use this one. So this will give me the result. The shape will be 1 to 8. That's good. From one query to the 8 documents. Just check this out. These are actually the similarity scores between your query and to each document coming from your corpus. The initial similarity score 0.13. Again, 0.13. 0.21, meaning that this document is more similar to query than these two documents, than another score. So I think this is the highest one, right? Yes. So meaning that this document, so index 0, index 1, index 2, index 3. The document located at index 3 is a document that is the most similar to my given query. This is how you can find, actually, we can look at here. Index 0, 1, 2, 3. as you can see, it received praise from astronomers for its scientific accuracy, so on and so forth. It's talking about how the science was accurate here, how science was precise. Yes, it's really answering my question. Okay, so this is how we can do it. Yes.
Sorry, could you also use large general embedding models like Boolean or OpenAI's API provided models for sort of stuff?
You can always use. It's always a dilemma that you should ask yourself whether I should use commercial APIs or I should use some open source models. There are some pros and cons, right? Using this kind of APIs is easier to use, easier to implement, and maybe working better depending on the model you choose, so forth. But on the other hand, there are some cons. First, you are paying some money. Secondly, you are sharing your information with these companies. If your data is some kind of private, or let's say that you are working with some patient records, that you should not share this information with this OpenAI, Google, or some other company, right? Because of the GDPR or some KVK in our country, so that you should not be using these commercial APIs in such scenarios, right? So that instead, you should develop your own environment. You should be using some open source models like in here, so that you will be in safe based on the laws. So it's a preference depending on the needs, depending on the cost, and depending on the scenario or the law limitations in your domain. Okay. Yes.
I have a question about this similarity with filters. At the very beginning, you mentioned that the accuracy and precise. Probably it's there is a number coming from pre-trained models like precise and accuracy are similar. So these end results are calculated based on the existence of accuracy in this document, or also the sequence of words?
The whole sequence, actually.
Yeah, it's not that simple, of course, but I don't understand how it works. Like I can understand word by word, but
actually, in order to answer your question, I want to go over here. Okay, look at here. Actually, look at that. Wait a minute. There's a problem. We have to go over here. Now, once you give your query, once you give your query here, so first you tokenize, these are each of these tokens are precise, the signs, whatever it is, correct? We just have these vectors coming for each token. And then what we're going to do, we're going to calculate here average, for instance. So we have one single vector to represent the whole query, okay? So we're going to have one single vector to represent another document coming from your corpus, another vector for another document, another vector for another document, so on and so forth. And then what we want to do here actually, we want to calculate dot product between these two vectors, just to understand how similar they are, okay? If you just calculate their dot product, actually like in here, you're going to calculate the cosine similarity score. If this is higher, it means that they are more similar to each other. Okay?
One question. I come from an R background. We are doing corpus 3, but in fact, in the vector, we are referring to the corpus. Yes, okay. 1 to 3, yes.
We call the side actually indices are starting from 0, right?
Yeah.
So that this is index 0,
yeah.
Index 1, index 2, index 3, all right? So if you go back here, if you go back to our corpus, this is a document in index 0, all right? This is index 1,
yes.
Index 2, and index 3. Actually, we found that this index is the most similar document to our query, so that I just retrieve index 3, right? Actually, yeah, that is the complex notation of this indexing methodology. I think if you can give a break,
Yes, yes.
okay, it's a good time for giving a break for 10 minutes, and now we will continue.
Oh, yeah, so you start using it myself, but like.
Yazacağım bu arada.
Okay, let's continue the second part. So before we give the floor to İnanç Arın for the second time, just a little bit of contextualization of things. Your group is a combination of very different backgrounds. There are full-on engineers, there are full-on computer scientists, there are people from sociology, economics, political science, who have different degrees of coding background. You all know coding one way or another, either through Python or R, but there are different levels of familiarity with programming and coding, and that is by design. Summer Institute in Computational Social Science usually gets people from all extreme backgrounds and basically put them together and see basically what happens. So the idea with these lectures is that they are deliberately, so for example, a valuable lecture like this, you won't be able to find it anywhere online in the way that this is being described. If you want to have some more like fundamental background lectures on this, we already have lots of recordings on basics of text analysis, basics of text mining, how to do term frequency, inverse document frequency. I put them on my website. We already did this backgrounder for the summer school in 2023. So if this feels like too advanced for you, there are already background videos and tutorials and trainings on the Summer Institute website, on my own website. The idea is to have such lectures that you won't be able to find anywhere else in recording. That is the whole logic of Summer Institute lectures that we're doing. And maybe in order to contextualize semantic search for people who come from social sciences background a little bit more, assume you're political scientists and you are doing a comparative quantitative analysis of political texts from different political parties or different parliamentary sessions. Or let's assume you come from psychology and you are basically trying to compare similarity of interview transcripts from people who have different psychological conditions, and you want to match which psychological condition matches with which other psychological condition by comparing text similarity. For those of you who come from sociology, for example, you might be comparing UNHCR migration and refugee documents across the years to see which UN refugee document compares to which other years. In order to be able to do that kind of document matching and document comparison, you need different statistical parameters and different statistical reasons. You start with text frequency, just count the number of words, then migrate into term frequency, inverse document frequency to see how term frequency adjusts in between each separate document. And then you start building into large language models like BERTs and everything. So semantic search is one of the most novel things. So there are tons of videos about BERT and Roberta online, but there aren't many lectures online, especially in the way İnanç Hoca is teaching right now. So every single lecture that we do in Summer Institute is the kind of lectures you can't find online easily, at least. So the logic is that we listen to these, take perfect notes, take these codes, take replication materials at home, try out at home. If you feel like this is still too much advanced, watch some beginner and training videos so that you build into a level in which this starts to make sense. But you know, Summer Institute is not incremental in terms of difficulty. We basically have lectures at dates and time slots where people are free that day. So you might have a very difficult lecture right now, followed by a somewhat easy lecture on Wednesday, and then a very difficult lecture on Thursday, and then an easy lecture. So the difficulty is not like incremental. We have lectures from all different backgrounds and difficulty levels. Just take all of the codes and replication stuff that you have from here and go back home. But semantic search is actually super useful for social sciences as well, especially for those of you who are dealing with large text data, especially large text data that spans across multiple documents. So for most of us, this is actually a goal line of the lecture. So, for example, thank you.
So the third part was actually the end of the first methodology, which was bi-encoder. Remember that there is another methodology, which is cross-encoder, that is also known as reranking. So what is the difference? The difference is this time in the cross-encoders, we're going to provide a query and the document together to the model. All right, look at here. First, we start with the series token, and then this is your question, then special separator token, and then this is one of the documents, for instance. All right. Again, anytime we have one more separator, then the question is, what is the similarity between that question and then that document? Right now, it will perform much better. Why? Because this architecture, this encoder model, will be able to see the question and the possible answer together, and it will see all of this attention mechanism, all of these relations, all of the context similarities all together, so that the result will be much more accurate, probably. If this is much more better, why we are not using this directly, why we are using the other one? Because it has a main drawback. The drawback is it is computationally much more costly, so that you cannot directly perform this application to the millions of documents. But this is real life. In real life, we are not, unfortunately, we are not searching on this kind of 8 documents. We are instead searching on millions or billions of possible documents. So that we are not using cross-encoders directly. Instead, what do? We first apply bi-encoder, okay? Because bi-encoders are fast. So as soon as you have 1 million document, you want to find an answer to among these 1 million documents. First, you're going to apply bi-encoder just to find some candidates of the answer. As soon as we're going to decrease this 1 million document to 100 possible candidates, and then in order to find what is the real answer, we're going to apply cross-encoder to these 100 possible candidates. So it will be a kind of qubit application within your progress. Okay, so cross-encoders never used, practically never used by itself in the applications. Instead, it is kind of implemented in a hybrid way with the bi-encoder. But if you want to get a good result, you must use cross-encoder because they are much more accurate. But they cannot be used itself, as I told you, so that you need to find a way to combine these two methodologies together. First, use bi-encoder actually to come here. Once you have huge number of documents here, let's say 1 million, apply bi-encoder just to decrease this into a small set of candidates like 100, and then apply cross-encoder just to find one single real answer. Okay, that is the main pipeline in a real-world semantic search application. So this is a hybrid application. As you can see, we are using both of the methodologies. So this is known as a hybrid application in semantic submission. Okay. So how to use cross-encoder? Actually, again, if you go back, sentence transformer official website, if you click on the reranker model right in here, you will see that again, you have a question, you have some possible answers, but what you should do here, guys, you should provide the model. By the way, this model is different than the others. But let me download this. Let me copy these two guys for you. Let me download this cross-encoder model. By the way, I made a mistake because again I have overwritten my own model. Anyway, it's not important. So while I'm using model here, this time I'm using my cross-encoder model. As you can see from the documentation, we should be using predict function. And it takes a pair. The first pair will be the question. The second part of the pair will be one possible answer. Okay? This will be your question, meaning that our query is a text, remember? This is one of the possible answers. Let's say, remember your query, it's called query. And one possible answer was first one, okay? Once you run this, it returns you a score. As you can see, it's a negative score, meaning that these two texts are not semantically related to each other. Okay? But if you try to calculate a more related answer, what was our which index? It was index 3, right? If you calculate this, as you can see, its score is a bit bigger than this, meaning that this is more related to that question than, okay? By the way, as you can see, we are still on the negative side. So that cross-encoder takes, although this is more related to this one than this, still these two texts are not perfectly matching to each other. Okay? So this cross-encoder, what it gives to me, that is the basic idea behind cross-encoders. Maybe you may ask, oops, not here. This. How these models are being trained? How people, all these companies, including Google, Microsoft, or maybe some other open source platforms, are able to create such bi-encoder or cross-encoders. Or whenever you have an open source model, how you can fine-tune that into your own dataset. So I will give you some examples. You need question and positive document pairs to do that. Let me give an example. Here, guys, I created 4 different pairs. The first pair, okay, question and document. Question, document, question, document, question, document. Each document is related to its own question. For instance, when was Interstellar released? It premiered in October 26, 2014 in LA, correct? This is the question, and this is the answer for that question. Let's look at here. This is another question. Who directed the film? Directed by Christopher Nolan, let's say. And then another question. How much did it gross? Answer will be worldwide growth over that amount of billions of dollars. So on and so forth. We're going to create such pairs. And then, let's come here. What model sees just for question 1? If you can remember, what was question 1? When was the Interstellar released? This is the positive answer. And by using all other answers, these are the negative answers. Directed by Christopher Nolan, no, this is not answer for this question. Worldwide goes over that amount of billion, that's not the answer for that question. So we just provide all of these answers to our batch so that our model will be able to understand, okay, whenever this question is given to our model, this is correct one, these are the incorrect ones, okay? So that it will calculate a loss function for each of these pairs. So what do we expect? We expect the loss function for the first pair should be quite small. Why it should be quite small? Because it's the correct answer. So this answer should be the answer. So this document should be the answer for this question. However, the rest should not be. However, the loss for this should be high. Loss for this should be high. Loss for this should be high. But loss for this should be small. So that your model will be fine-tuned. It should be changing weights or so forth accordingly, so that in the long term, your architecture will be working fine on your own data set. So whenever you extract or you take some open source model or some OpenAI's commercial APIs, it was trained on general data sets. In some cases, you may be working on very niche, very special domains, very special data sets, so that these models may not be able to run perfectly on your data set, on your problem. So what you may need, but be careful, this is not all the time needed. In some cases, if your data set and domain and problem is quite different than the general knowledge, then you have to fine-tune your model to your own problem, so that your model will be able to predict much more accurate results for your own data set. For that reason, this fine-tuning approach can be important if you are, especially if you are searching or if you are working in social sciences. Sometimes I know that you work in very different subjects, very rare concepts that these models may not be able to understand, so that you may need to fine-tune. Sorry, yeah.
For real case scenarios, how should we know if a general large language model is enough or not? Is there a gold standard that you can compare the results, or maybe we should?
Yeah, there are some metrics. Okay, probably we will not be able to cover it in the picture. If you look at end of this lecture notes, you will see some metrics that you can use. Right. So these metrics are important because whenever you have a different problem and you have a model and you have a problem, right? We want to test whether this model is working fine this problem, so that we can apply these metrics. If these metrics are working fine with this problem, okay, we are safe. We can directly use these models. On the other hand, if this model is not able to make good predictions for my own problem, then something's wrong. So what should I do? I should either change the model, maybe I can use another model which can perform better, or I may need to fine-tune my model just to make it better. Maybe I can search for some other options, some other options. But yeah, the answer for your question, yeah, there are some metrics, there are some benchmarks that you can use in order to understand whether the model is good for your problem or not. Yeah. Yes.
I want to ask something about negative outcomes. We checked some negative outcomes previously. For example, from our first question, how accurate is first is? What if there's a document saying that it's completely inaccurate? For example, does it give a negative score? Or are we seeking for absolute value?
Actually, the thing is that providing this, okay, think about this negative, right? We have positive answer and negative answers. You need to prepare these answers in a way that your model should be able to understand that in a better way. If you just provide easy answers like that, then the model will not be able to learn it good. Let me give you an example. That's a good question. I was going to show you in a moment. Look at here. We have some easy negatives and hard negatives. To be honest, easy negatives are not so useful. For instance, look at here. if the question is, what is the capital of Australia? Okay, the answer is, the correct answer, Canberra is the capital city of Australia. For an easy negative, for that given question, the answer, let's say, photosynthesis converts sunlight into glucose, some unrelated answer. Okay, I know that this is not the answer for that question, but providing this negative sample will not so useful for our model. Instead, you should provide some hard negatives, like here. Okay, see, again, correct answer is Canberra is the capital city of Australia, but look at here. Another negative answer is something related to Australia, but it says Sydney is the largest city in Australia and a major hub. Okay, this is not the answer, exact answer, but it's some kind of related to the current concept so that we consider them as a hard negative. Right? So you should provide such hard negatives into your model so that your model will be much more advanced. So it will be able to make predictions in a much more accurate way. So what Microsoft does, these guys are quite clever. So I don't know whether you use Bing or not. Okay, even if you don't use Bing, you use Google or some other search engine. Whenever you make a search on Google or on Bing, you got some set of results, right? These are some possible candidates for a result. But you click on all of them, maybe two of them, all right? So these clicked ones will be the correct possible labels. The unclicked ones, they are not unrelated. They are just some canvas for your question. They are related, but the user did not click to that website. So Microsoft uses the unclicked results as hard negatives. So this is the way how they develop their own models. Since, by the way, they have huge data, like Google. For that reason, whatever Google provides, whatever Microsoft provides, they do something better than the other companies. Why? Because they have some kind of very valuable data. Because millions of or billions of users are using this company product every single day. And these companies are collecting some very important data that we can never achieve, we can never access, unfortunately. Okay? But I believe you understand basics or fundamental behind this. So the data that you are using to create such model is very important. That can influence the performance of your model. Right. So, any question?
Actually, I have a follow-up question. I'm thinking in terms of statistical terminology. So, for example, -11 and -9, we have to compare those two numbers. In terms of correlation coefficient, for example, -0.11 is in absolute value terms larger than -0.9, and it implies more inverse relationship. So it's stronger in terms of statistical notation. But in your case, you're saying that -0.9 is better. So it's kind of implying more relationship with each other. It's kind of different in terms of statistics, right?
Yeah, it's different.
Did I get it correct?
No, I understand your question.
Yeah.
So cosine similarity gives you a score between -1 and +1, right? So it can be actually this is what it does, but cross-encoder gives you a different result. It can be -11, -9, so, but you can actually use a very special function just to convert in -1. Here the thing is that it's not about the absolute magnitude. It's about how positive it is, right? So as you get close to the minus or +1, all right, it means they are more related to each other, okay? As, for instance, if your score is 0.03, if one score is this. If the other score is -0.9, it doesn't mean that the second score, the second tempo is more related than the first tempo. No. Since its value is greater than this one, the first one is more related than the second tempo. Okay? It's not about the magnitude, it's about how big, how they are close to positive, or how they are more positive in our system.
So that's why you call it loss function. It's kind of additive.
Exactly.
Yeah.
Exactly.
I have another question about that. So, okay, so we are not taking for absolute 1 year. I understand that, but can you tell me that, for example, the similarity between like opposite words, like accuracy and inaccuracy, for example, let's say that there's a document that this movie is completely inaccurate, then what will be the number?
Score will not be so negative because you are trying, accurate and inaccurate. Although they have opposite meanings, this about something about performance. So they are still related to each other. But of course, the score will be lower. All right. Okay. If you probably if you calculate precise and accurate, it will be more close to each other. But inaccurate and accurate will not be direct related to each other. They are still related. But of course, there are some. You have some kind of deviation in your direction. However, still they are not unrelated. I cannot say that.
But still, we will always have the positive result before the negative one. Like the accurate one will be always compared. But how we will know that that's the answer we are looking for?
Actually,
Actually, inaccurate.
think about the nature of these transformer models, right? About these large language models, within the context, it understands what is the relation. It can be a positivity or negativity relation, it can be a sentiment relation, it can be some kind of context relation, it can be some other kind of relation. Okay? These models are able to capture whatever the relation it is within your given question or answer. And then based on this relation, I will not, actually, I can explain this to you in 2 parts in a different technical detail, but what I want you to know about is what these models are capable of understanding the relation between each of these words, whether positivity, negativity, sentiment, whatever it is. And then based on this relation, it will make some calculations accordingly and then give you the result based on these relations.
Yeah.
Okay, I think I mentioned about all of this stuff. So that, as I told you guys, in a real-world application, we generally have 2-stage pipeline. The first stage will be using bi-encoder, because bi-encoder works really fast for 1 million documents per minute. On the other hand, for stage 2, we will be using cross-encoder. Be careful, cross-encoder takes more time because it's more complex. So that is we first use bi-encoder just to find top 100 candidates from millions of documents. And then from these candidates, we're going to apply cross-encoder just to find final output of our semantic search application. This is the final real-world professional pipeline in today's world. Okay. Now, what I'm going to do, guys, I want to go back again to my, but this time I'm going to change something here. I don't know whether you are using Colab or you are doing this in your own computer. You need to change the runtime. Because by default, Google Colab allows you to use the CPUs. But this time, I want to use GPUs. All right. Just click on this one. By the way, do we have time for this? Maybe we, okay. I just want to show you something. Maybe I can show you from, not from scratch, but from the prepared code. But if you want to do all of this stuff, I want you to change runtime to GPU, okay? It will be working faster. But this time, I don't have enough time. I just want to show the dataset I'm going to use here.
You have time, hocam. Yeah, we are flexible. We are flexible. How much more time? We are flexible.
Okay, how flexible you are? Well, I want
How flexible should I be?
Okay, maybe it's better if I show this on a prepared code, all right? So look at here. I already said, 2 different data set, test and validation. But more importantly, what do I have in each example? This is just one sample. What do we have here, guys? We have actually And ID is not important for us. The title for that question is that familiar to you guys? Area 51? Have you heard about this? Do you believe in actually footballs or aliens? Anyone here? Raise your hand. I believe to be honest. Trump. So please, I don't do that. Okay, anyway, there are some rumors about the Area 51 that people ask too many questions. Government, sometimes they reply, sometimes they do not, but anyway. So the question is, there's a question here. Who analyzes the biosynthesis? That is the question. And here we have a context. So there's an answer to that question within that text. The answer is here. Rutgers University biochemists, right? So the answer of this question is this one, but this answer is given in that text, right? You can check another example. This was the index 0. Let's look at index, let's say 10. I don't know. Again, another question related to area 51. Who was developed for the initial U2 delivery, right? Again, we have another context. Within that context, we want to find the answer of that question. Answer is actually here. Lucky technicians, something. There are some other type of questions here. Let's say index 1000. Even I don't know how to spell this pronouncement, to be honest. Anyway, so the question is, what does cosine mimic? Right, this is the question. From that document, from that context, I think it's some kind of medical term, correct? From that context, I want to find the answer of that question within that. That is the question. So, as you can see, we have different contexts, we have different questions, and we have thousands of them, right? So, what I want to do here, I want to find, okay, sorry,
For next example, what if, for instance, clonidine mimics two different things? Then they would have two answers.
No,
just
if
one.
this guy has two different meanings, we have to understand which one it is, right? So by looking at the whole context within that sentence, we can understand which meaning it carries within that sentence. Remember the bank example. It might have a financial bank, right? That we just deposit some money, withdraw some money, so on and so forth. We might have another meaning, river bank. It's a geographical place, right? How we can understand this? By looking at the surrounding words. The model will be able to understand which context it has with the given sequence, right? And here, okay, maybe clonidine has different meanings. By looking at, for instance, mimic, probably if you capture that word with this clonidine, it will be able to understand in which context it was used within that sentence, right? By looking at surrounding words, these large language models are able to understand its real context. That is that. So, I have thousands of contexts. I have thousands of questions. I know that for each sample, this question is related to that context. But for some other sample, look at here, this question is related to that context. However, this question is not related to that context right here. So what I want to do, I want to actually say all of these contexts in a database. Okay, they do not see the questions. I just separate them all of these contexts, thousands of them. Actually, there are 10,000 questions here. And then whenever I ask a question separately, I want to find related context information from my database. Okay, that is the idea. So again, if we come back here, look at here. This is the number just for coming from that data set, 11 more than 11,000. So that whenever I ask a question, I want to find the related context from these 11,000 samples. That is the idea. And first, I will start with bi-encoder, see the performance, and then I will combine bi-encoder with cross-encoder. I will see the second result, and I will check whether the accuracy was improved or not, right? That is the idea. In order to do that, I'm going to share screen together with you, right? Don't worry. Okay. Let me go over this code one by one, all right? So it will even take some time. First of all, I just change, okay, until so far it was the same. I just change tree the names. It should be tree, it should be test. This is the general convention we use in data science, right? So this is what I did here. So at the end, as you can see, I have train data and test data. Within a train, I have this number of samples, 11 more than 11,000, right? And now what I want to do here, guys, look at here. I have a loop here, guys. There's a progress bar. That's why I have imported 2QDM library in order to see that progress in my application. I use some batches because for some efficiency problems, I do not process them one by one. I process them batch by batch. Within each batch, I will have several examples. For instance, here, my batch size is 100, meaning that within each batch, I'm going to process 100 samples at the same time. You can process them one by one. As I told you guys, this is just for efficiency reasons. Right? Just I want to process them in much more efficient way. So, in a loop, I will process a different batch. So look at here. I'm gonna get the sample from the tree. If I is 0, I will get first 100 sample. If I is 100, I will get next 100, and then next 100, next 100. I will go down one by one, right? And then I just get the context. I only get this information from the samples. I don't get the question, but I don't want to cheat here, right? I just want to get the context information here. Okay, get the context. And like we did before, encode this batch into embeddings. Don't forget normalizes. Normalization is very important. And then store them in a one single list, right? At the end, I'm going to store them in one single list. Actually, the length of that list will be the batches, right? So within that list, actually, I will have, what I'm going to have here, guys, I'm going to have the vectors of each batches, something like this. This is actually the structure of the current all embeddings. This is the first batch, second batch, third batch, fourth batch. Depending on how many batches I have here, I store them as batches. However, in order to proceed further, I have to change this structure into this structure. So it should be like this. So since I process them within batches for efficient reasons, I got that result. However, I should have that result in order to proceed further. How can I do that? In order to make this conversion, there's a very simple function in NumPy. NumPy vertical stack, right? Just convert that version into that version. That's it. And then I'm going to use a very famous indexing library, FAISS. Actually, as far as I remember, it should be fast index search, or fast index semantic search, something like this, okay? This is the abbreviation of this. So I'm going to create an index here. This IP means inner product. Remember what was inner product? We just calculate inner product to calculate the similarity between different tokens, right? So you need to provide here the dimensions of your vector. Before you create your index, FAISS wants to know what is the dimension of your vectors. Remember, it was 768 or 384, depending on which model we use. We need to provide dimension here. Initially, the number of total documents in our index is 0. We want to import all of these embeddings into that index. How are we going to do this? By using add function. Okay? If you're going to use add function, as you can see, I want to add or import all of these embeddings in that index. And then, as you can see, this is the number of documents stored, by the way, sorry, not documents. This is the number of the vectors stored in my index. And then, what I want to do, whenever I ask a new question, I want to find the most similar documents coming from that index. Among all is more than 11,010. That is the part. So, let's come here. What will I here? Actually, this is my experiment part. I will basically explain you what I'm doing here. For each document coming from my train data, this time I'm getting the question. Remember, in the previous part, I retrieved the contexts without the question. I embed them, convert them into vectors, and store these vectors in my index. This time, I'm getting the question. Once I get the question, I say that it's query. Convert this query into embedding. Normalize this embedding by using again the same formula here. Okay, I get embedding. And then I want to search this vector, and I want to find the most similar 5 vector coming from this index, right? Once I will get candidates here, I got the initial result. Actually, if I say K1 is here, it will not make a difference here, because right in here, I will get the most possible candidate according to my encoder, and I'm gonna say, if this most possible candidate is same with the current index, it means that I have found the real answer, okay? For a given question, I was able to find the real context of this question and increase count by 1. The count is initially 0, and I'm doing this for my sample size. You know what? At that, unfortunately, I don't see the result here, but I remember that the result was here, guys. Accuracy was 0.38, something like this. So that with 38% possibility, I was able to find the correct result by just using bi-encoder. Okay, this is the performance of bi-encoder. Among, let me repeat, among more than 1,000 possible pairs, if you want to find the real answer of a question with 38% of chance, you will be able to find the real answer. I don't know whether it is satisfactory for you or not, depending on the context, depending on the complexity of the questions, and so forth, but we can make this better. Or we can make this better by using a qubit approach. What the qubit approach here, guys? Qubit approach, right in here, actually. Wait a minute. Qubit approach, right in here means whenever you got the results from bi-encoder, do not directly use them. Look at here. We get the possible 100 results from bi-encoder, but from the possible 100 results, we apply a reranker. Okay? So rerank that by using cross-encoder, so that hopefully I will be able to find a better results. Because this is much more complex, this is much more slower. However, I do not apply this to whole document. Instead, I apply this to only 100 candidate samples. So once I run this, look at the increase in appearance. From 38%, I increase this into 54%. 18% of increase in my parameters. So this is the effect of cross-encoder. So, to conclude, so in professional life, professional data scientists, actually, I work with a lot of them. All right, in not only academia, I also give a lot of consultancy to the companies about this data science, about large language models, and so forth. I work with their real-world data sets. All of these companies have different problems. all of them have different data sets, different complexities, so on and so forth. Of course, depending on the problem, we fine-tune the model a little bit. We just change this solution slightly different than each other. However, the most of the time, the methodology is the same, right? So if you're a professional data scientist, or if you want to apply some kind of professional data science methodologies, you should follow what can I do further in a much better way. Okay? Using bi-encoders is good, but may not be enough. If you combine now with cross-encoder, it will be much more better. There are some other more advanced methodologies. You can search for it, but I think it's enough for today's lecture. So what is important, guys? As a guy who is working in LLM domain, to be honest, I'm quite tired just to try to catch up all of these developments every single day. I believe that it's not possible to follow all of these single documents one by one. Because at the beginning, okay, in 2022, in 2023, I was more optimistic. I was trying to catch all of these developments that was released every single day, but after some time, it became infeasible. What you should do, all of us have different interest areas, right? You are interested in maybe social sciences, maybe some of you guys are interested in data sciences, and whatever you are interested in. Just try to follow the latest development just in this area. But try to follow, because every single week, every single month, you get a new methodology. You know what? Applying the methodology which was found 6 months ago may not be enough for you. Okay? This is today's world. This is the reality. So that you have to keep yourself updated. This is what I suggest to you. I'm doing myself. I'm doing this for myself, and as I told you guys, I'm very tired of this. So that I became much more and more selective. So that maybe on every single day, I try to read different papers. Like recently released papers, like 1 week ago, 2 weeks ago, so forth. But there are many of them. So just try to be selective. So there is no base paper for all of us. For some of these papers can be best for me, but for other papers can be best option for you guys. So that you are the expert, you are domain expert. What is related to your own study? So I think this can be the end of my presentation. Any questions that you might have, I would like to more answer.
Yeah, you said you have to follow up, but which other sources do you recommend? Okay, we said articles, we can follow articles, but do we have any other sources that we can follow, like maybe websites or email the lists? I don't know, YouTube videos.
For instance, do you know bi-encoders?
Yeah.
No? This is a platform that people share their data sets, their models, their any kind of work about large language models on that platform. It's open source. Okay. In bi-encoders, there is a find about trending papers on every single week, on every single. I mean, in 2 or 3 days, I check that. Okay. What is the latest papers released and which of them are trending? Okay. There are a lot of them, to be honest. I try to be selective about these papers. I read them, first of all. Secondly, maybe it will be funny, but I use Twitter a lot. Twitter is my major source for this because Twitter algorithm is quite good. Right now, my algorithm is converged into 2 main subtopics. First one is football. Second one is about large language models. So I follow some important people. I mean, the algorithm knows me. Whenever a new development exists, it just shows this post to me, and I direct, okay, there's a new development here, every single day. Yeah, to be honest, Twitter is one of the major platforms that I follow all of these developments. There are some important people that you may follow over there, okay, because they, every single day, every single 2 days, they share the latest developments with papers, with applications, and so forth. You can follow them as well.
Can we follow you so we can follow you? So
Of course, follow me, but I didn't do. I'm on the reading part. I do not share it too much, right?
So just to find who are your followers.
Of course, you can do that. Just follow me, İnanç Arın. This is my Twitter page, name and last name. You can do this. But most of them will be football adults. Anyway, yeah, this is the way. Apart from that, you can always reach me out. I can try to help you, especially from the technical part. So I know these large language models from the technical development. I teach such courses. I give consultancies from that perspective. I don't know your domain. I may not know your domain about social science and so forth, but I had some experience. Let me share one of them. I worked on a hate speech project with Branding Foundation in Turkey. So the problem was we have a lot of tweets and we want to predict whether a given tweet contains hate speech or not. We figure out that hate speech is a very subjective matter. For a given text, for some it can be hate, for some it may not be. First, we need to define what is hate speech, how we can define them, how we can categorize them, what are the levels. I mean, it's not only about binary, it's hate speech or not hate speech. It's not the case. There are different levels in the hate speech. So we just developed different benchmarks, different models on top of that. This was one of the interdisciplinary projects with the social scientists. The other one was about after 2014, as you know, a lot of immigrants moved into Turkey from Syria, as you know, refugees. I made some studies on refugees as well. Again, it was about Twitter data. We collected thousands of tweets about the refugees, and we made some analyses about the problems, about the perspective from the Turkish nation, about some economical perspective, about social perspective, adaptation perspective. There are different problems that these people and the country has. I also did study on this kind of social science related problems. So I like to work on this kind of interdisciplinary projects all the time. So for that reason, what you are doing here is great, to be honest. So we should find a way to combine social scientists and data scientists together in the same platform, and we should allow them to work together with the same studies. And future will be actually interdisciplinary project, in my opinion. So keep track of that. Thank you very much, guys. I'm very happy to be here. I think we can make sure.
Yeah, let's go for lunch. Before lunch, let's take a photo with Inanç as well. We can maybe invite someone who is not from our end. Yes, so that we can all let's check the next.
Çıkıp